Homework last night was on page 819. This related to fission and fusion and the energy that's released as a result of a fission and or fusion reaction here. We're going to do number 2 and 3. They kind of go together. Number 2 says the uranium-235 nucleus absorbs a neutron and then splits into bromine and lanthanum. This is the same element that we started off with in our example yesterday, right? Uranium-235, and it undergoes fission by absorbing a neutron, but it's decaying into 2 different nuclei. Yesterday, I think it was krypton and barium that the uranium-235 decayed into, and today it's bromine and lanthanum. That's okay, and we do it the same way. This time we have to actually write out the reaction to figure out how many neutrons are released in the reaction and balance it, and then we have to figure out the energy that's released in that reaction. So let's write it out here now. We start off with a neutron and a uranium-235. Now, it's important that the neutron and the uranium are on the same side, but is it important that we put the neutron before the uranium? There's no reason that it has to go in this order versus the other order. There is a very clear reason why the neutron has to be on the left-hand side. It's absorbed. If the neutron was given off, it was some kind of fancy neutron decay, then the neutron will be on the right side. But if it's being absorbed, it's got to be on the left side as a parent, or as a, if you think in chemistry terms, a reactant. Now, what do we got on the right-hand side? We got bromine 87, 87Br, with an atomic number of 35, and we've got 146 La with an atomic number of 57. We got to make sure that, first of all, the bottom number matches up. That's the atomic number. Using the law of conservation of charge, 0 plus 92 is 92. 35 plus 57 is 92. Perfect. Okay, conservation of charge already works for us here. Now let's look at the top number, and we're going to use the conservation of nucleons for that one. 1 plus 235 is 236. 87 plus 143 is 233. 146, I should say, is 243. 233. How many neutrons do we need? How many neutrons do we need here in order to balance that out? Eric? We need 3 neutrons. That's what we needed in our example yesterday as well. And I'll be honest with you, that's often what it works out to be in these fusion reactions, but not necessarily. Don't assume 3 neutrons. I've seen them where they need 2 neutrons, before. Sometimes it might need a different number of neutrons than 3. So just be careful of that. Don't assume that it's automatically 3. By the way, we're also releasing some energy over here, and we'll find out what that energy is in question number 3. All right. That energy that's released, where does it come from? Where does it come from? Okay, we haven't just created energy from nothing, but we do have energy that we didn't have before. Right? Good. Comes from mass that's been converted to energy. Perfect. And what's that term that we call the mass that's been converted into energy? Yep. Good. It's the mass defect. We defined mass defect yesterday in 2 different ways. One was in the context of a nucleus, a single nucleus. It was the difference in mass between the nucleus and the nucleons. Okay, the nucleus weighs a little bit less than the nucleons. The other way we define it is the difference in mass between what we start with and what we end with, the products and the reactants, the daughter nuclei and the parent nuclei. And that's what we got to look at here, the difference in mass between what we start with and what we end with. To do that, we got to find out what the mass of all of these things are. What was the mass of a neutron given to us on that table in atomic mass units? We're going to want it in atomic mass units because the rest of them, like these ones, aren't given to us in kilograms. Now, Carrie, odds are on a test, these numbers are going to be given to you in kilograms as opposed to atomic mass units, so we're not going to have to do that conversion. We just do exactly the same thing, except not bother with the conversion. Okay? If we got it in kilograms, even better, but if we don't, then we got to go with the units that they give us, like in this case, atomic mass units. Jacob, what is it? Okay, that's atomic mass units. And what's uranium-235 in atomic mass units there? Victoria, you got that one? 235 point. 043930. Thank you. Now let's get the right-hand side. We'll go with the green ones here. Bromine 87 is going to be how many atomic mass units there? Thank you. And LA 146. Hannah, what's that one? And 3 neutrons is going to be 3 times 1.008665 atomic mass units. Somebody yesterday asked me, somebody in the afternoon class yesterday asked me where I got those numbers from. Those numbers all come from the table that's photocopied in the notes that I gave to you. It's also this table right here. Do you need to know those numbers? Of course not. I don't remember those numbers. Okay, that's like remembering pi to 50 decimal places, right? It's yeah, like, hey, that's neat if you can do it, but it's in the end, it's useless, okay? You'll be given those numbers. It wouldn't likely be in the form of the table that it was given to you here. It would more likely be buried in a page of information, but those numbers would be given to you if you needed to do a question like this. All right, I want this side of the room, Caitlin's side of the room over. You guys are going to do the green ones this time. Jacob's side of the room over. You guys are going to calculate the blue ones for me, please. Ben, what's the right-hand side there? 887. Thank you. I'm going to square that off. Guys, listen, do you have to write it, show it in the exact structure that I'm showing it? No, of course not. But is it important to have some structure in a question like this? Sure, it absolutely is. We got a whole bunch of numbers floating around with a whole bunch of decimal places floating around here. And if you don't have some kind of structure, then you're going to make a mistake. You're going to mix up one of these numbers here, okay? So what I'm doing here is the total, I'm just squaring it off, okay? If you want to write it differently, go ahead, but make sure you can distinguish the total from all of these other numbers that I have floating around here. What's the blue number on the left-hand side, the total mass on the left-hand side there? Ben? Thank you. And that is a bigger number than we have on the right-hand side, which is what we'd expect. That's where the mass defect is, right? That's the difference in mass between the reactants and the products. The products always weigh a little bit less than the reactants. Now let's get the mass defect. And this mass defect is going to be in atomic mass units. Although, if it's on a test and you're given these numbers in kilograms as opposed to atomic mass units, then your mass defect would be in kilograms as well. What do we get for that mass defect? 236.05 minus 235.87. Carrie? I'm sorry? Oh, this one isn't 235.872. No? That is right? This is right? Okay, Carrie, try that one again, okay, just to make sure. What do we end up getting for the mass defect, OR? 180098. As you can see in this question, particularly in this question, how important it is to keep multiple decimal places, right? Usually I say keep 4 or 5 decimal places until the end. In these ones, keep them all, every single one of them, because the difference in mass is so tiny, okay, it's critical that we have right up until the last decimal place there. All right, now we want to convert this to kilograms. So we're going to say 1 atomic mass unit is 1.66 times 10 to the minus 27 kilograms. And that conversion factor is on my data sheet. 0.180098 atomic mass units is equal to X kilograms. Solve for X. X ends up being how many kilograms there? Okay, Jacob? So we're dealing with an incredibly small mass defect, an incredibly small amount of mass missing. Now, it doesn't take a lot of mass to make a lot of energy, because E is equal to mc squared. When you start squaring 3 times 10 to the 8, a little bit of mass becomes quite a lot of energy pretty quickly, right? So let's take that mass defect, 2.9906394 times 10 to the minus 28 kilograms by 3 times 10 to the 8. Let's square it. And we end up getting, in joules, Jacob, you got it? (2.69 times 10 to the minus 11 joules. Now, that's fine. Joules is fine. But they give it in mega electron volts here. Let's say that this is a test question, and you have 4 options, and 4 options are all given to you in mega electron volts. Okay, and we got to convert this. Let's do that now. I'm fine with joules. Okay, if they want mega electron volts, then that's what we got to do, though. We know that 1 electron volt is equal to 1.6 times 10 to the minus 19 joules equals X electron volts over 2.69 times 10 to the minus 11 joules. When we do that math, that should give us 1.678 times 10 to the 8 electron volts, which is 167.8 mega electron volts. Now, that might work out to be slightly different because Jacob gave me the rounded number there as opposed to the unrounded number, but you get the idea there, right? Good? How many people got that? Okay, not a ton. Are we okay with that? We don't see a question like this all that often on exams, but it's not like it's appeared once in the last 20 years either, okay? It's certainly more common than that. It's not one of those ones that I would say, you know, like, I mentioned the Michelson rotating mirror experiment. Since they put that in the curriculum 9 years ago, that's always there, almost always there. Out of the last 18 exams, it's been there probably 16 times. We can expect to see that, right? This one, I would say, you know, 40, 50% of the time. It's not one that we expect to see, but it's certainly one that we could see. Except that I doubt you'd have the atomic mass units. I think it'll be kilograms if you do see it, but you never know. Right? There's a couple multiple choice questions that I'd like to work on here right now. The first one being 166. This one's going to go pretty quickly for us, and it's going to be pretty familiar to you. Take about a minute at your desks right now and see if you can do that one. All right, what do we got here? It says, in 1939, 4 German scientists, Otto Hahn, Lise Meitner, Frank Strassmann, and Otto Fisch made an important discovery that ushered in the atomic age. They found that the uranium nucleus, after absorbing a neutron, splits into 2 fragments that each have a smaller mass than the original nucleus. Right? Mass defect, right? This process is known as nuclear fission. And here's a couple of different possible fission reactions here. Here's the one that we used as our example in our notes. Here's a completely different one. Both uranium-235 absorbing a neutron, but different possibilities, as you can see here. We want to find the value of X in reaction 2. That's the coefficient, right? That we're just trying to determine how many neutrons we need in order to balance this equation. Using conservation of charge, using conservation of nucleons. All right, well, we start off on the left-hand side with 92 and 236. On the right-hand side, we have to have 92 and 236. But in the absence of these neutrons, we have what? Well, we have 54 and 38 is 92. 140 and 92 is 232. All right, what are we missing here as far as neutrons go? 232 plus 4 gives me 236, 92, and 0. We can't have an element that's 0 and 4, so rather what you have is 4 neutrons. So the answer would be A. How many people said A? Good. All right, we'll give you a couple minutes to take a look at number 167 and number 168, please. All right, the question says the measurements given below indicate the uranium-235 nucleus has a smaller mass than the mass of the corresponding number of protons and neutrons. So look, we've talked about mass defect as being defined in a couple of different ways. One in the context of a single nucleus, one in the context of a reaction. We've done a couple of problems where we found the mass defect and therefore the corresponding binding energy in the context of a reaction, but now we're doing one in the context of a single nucleus. Here's the protons and neutrons, here's the nucleus, they weigh something different. Now, we want to find out what the mass defect of uranium-235 is. So, what are we going to do? Let's get the mass of the nucleus. Well, good news, we've already got it. The mass of the nucleus is 3.9021 times 10 to the minus 25 kilograms. We should expect to see the mass of the protons and neutrons combined slightly larger than this. Not much, but slightly larger than this. Now, I suspect what some of you did when you found the mass of the nucleons is added the mass of a proton and the mass of a neutron and got a number that was completely different than the mass of the nucleus. That wasn't bigger than the mass of the nucleus. How many people did that? How many people added the mass of a proton and neutron? What do you got to do? How many protons do we have? You can't just say, I got one proton and one neutron. That would be an isotope of hydrogen, not uranium. You can't just add 1.67 to 1.67. What we got to do to find the mass of the nucleons is add 92 of these and 143 of these. Does that make sense? The total mass of all the protons and all the neutrons combined. How many people did that? Okay, Ali, what did you get for 92 times that? 1.53. Thank you. And Ali, what did you get for the second one there? Thank you. And the total there? 3.9338 times 10 to the minus 25. Good, thank you. Now we take a look at that number, 3.933899. We take a look at this number. The mass of the nucleus is slightly less than the mass of these protons and neutrons. The mass defect is the difference in mass between those. So we're going to take this number, we're going to subtract this number, and then we're going to get our mass defect in kilograms. All right? What do we end up getting there? 3.18 times 10 to the, I guess, yeah, makes sense, negative 25. So we'd express that, since we're only looking for the value of B there, we'd express that as 3.18, right? Yeah, okay. Well, we know that uranium-235, it doesn't tell us how many protons it has, but uranium always has 92 protons. We know that by looking on a periodic table. We see the atomic number is 92. As far as 235, as far as 143 neutrons, well, we know the mass number is 235. So if there's 92 protons, 235 minus 92 has to give me 143. Does that make sense, Gary? The atomic number, even if they don't give it to you, is always on your periodic table. The number of neutrons, you got to figure that out from the atomic number and the mass number that they have to give to you. All right, you want to find the binding energy? All right, this one's the easier of the two questions. All we're going to do is say E is equal to mc squared here, right? That's whatever the mass defect was, 3.18 times 10 to the minus 25 times 3.00 times 10 to the 8. Don't forget to square that. Don't forget to square that. And I'm not sure what it works out to be. When you get it, it's going to be in joules, and then you got to convert it to electron volts by doing 1 eV over 1.6 times 10 to the minus 19 joules. What do we get, by the way, here in joules there, Ali? So we can do the conversion. What is it, 2 point? Anybody have it in kilograms there? Okay, we'll just say it's something. Okay, it's something. So we're going to say, look, we got the value in joules, whatever it is, something. We're going to find the value in electron volts just by cross multiplying. Okay? And what do you end up getting for the final answer there? I got 2.86. Yeah. Anybody else? Somebody else get that? Yes? Good. Thank you. 2.86 electron volts. Is that times 10 to the something? 10 times 10 to the negative 10, but of course, we're only looking for the base there. Good.